Welcome to Deep Learning Foundations, where we cut through the hype to reveal the core concepts powering today's most advanced AI. Artificial intelligence is everywhere, from your smartphone's voice assistant to self-driving cars. But what truly underpins these revolutionary technologies? Today, we'll demystify deep learning, distinguishing it from broader AI, and dive into its fundamental building block, the artificial neuron. At its highest level, artificial intelligence, or AI, is the expansive field dedicated to creating machines that can simulate human intelligence. This includes everything from problem-solving to understanding natural language. It's the overarching goal of making computers smart. Nested within AI, we find machine learning, or ML. This is a specific approach to achieving AI where systems learn from data without being explicitly programmed for every scenario. Instead of hard-coding rules, you feed an ML model data, and it identifies patterns and makes predictions. Deep learning is a specialized subfield of machine learning. What makes it deep is its use of artificial neural networks with multiple layers, drawing inspiration from the structure and function of the human brain. The deep in deep learning refers to these multiple hidden layers within the neural network. Unlike traditional machine learning models that might have one or two layers, deep learning architectures can have dozens or even hundreds of layers, allowing them to learn incredibly complex patterns and representations from data. At the very heart of any deep learning system lies the artificial neuron, also known as a perceptron. Inspired by its biological counterpart, this simple mathematical function is the fundamental processing unit of an artificial neural network. An artificial neuron works by receiving multiple inputs. Each input is associated with a weight, which represents its importance to the neuron. These inputs are multiplied by their respective weights, and the results are summed together, often with an added bias term. This weighted sum then passes through what's called an activation function. The activation function introduces nonlinearity, determining whether the neuron should fire or be activated, and what its output should be. Without these nonlinear functions, neural networks would only be able to learn linear relationships. The output of a single artificial neuron, after processing through the activation function, is typically a single numerical value. This output can then serve as an input to other neurons in subsequent layers of the network, or it can be a final prediction. The importance of these artificial neurons cannot be overstated. By connecting many such simple neurons into layers and networks, deep learning models gain the ability to learn highly intricate patterns, process vast amounts of data, and perform complex tasks like image recognition, speech processing, and natural language understanding with remarkable accuracy. From a single neuron, we scale up to artificial neural networks. These networks are organized into layers, an input layer to receive data, one or more hidden layers where the complex processing occurs, and an output layer that delivers the final result. Understanding the artificial neuron is key to grasping the power of deep learning. It's the basic computational engine that, when combined in vast, interconnected networks, enables the sophisticated AI applications we see today and forms the foundation for future innovations.